Okay. So the last section of notes that we did was over rates of change in tangent lines. And we were given a function, then we had to find the slope of 2 points on that function to be able to estimate the slope of the tangent line. When we're looking at the limit, some of that work in the beginning is done for us. We're going to be asked to find a limit of something that looks like what our slope formulas look like. So we won't actually have to calculate the slope anymore. That'll be kind of done for us. So the notation for taking a limit it's going to look something like this. The limit as x approaches 1. So you write limit and then really small underneath as x approaches 1. So x with the arrow going to 1. Of 2 minus 2x squared over x minus 1. So this is what we're going to be given and asked to find this limit. This is the same as one of the examples that we did in the last section of notes. So we were given find the equation of the tangent line to this function at x equals 1. And then we had to find the formula for the slope, which is this 2 minus 2x squared over x minus 1. So all this notation for the limit has done is taken this part from this problem, this 2 minus 2x squared over x minus 1, and this x equals 1 that we were given, and it's turned into this notation. The limit as x approaches 1 of this equation. Okay, we also, and then what we found that to be was -4. So we already did the work to find this limit because we did our chart and we got all the numbers, and those numbers were approaching -4. So that means the limit as x approaches 1 equals -4. Okay, another example that we did, if we were to write it in this notation, the limit as t approaches 5 of t cubed minus 6t squared plus 25 over t minus 5. So that was this example about the amount of air in a balloon and how quickly the volume was changing. We had to find this equation using the function that we were given. And then we were asked to look at the change of the volume after 5 hours. So we were given that 5. We did the chart. We found that the values were getting closer and closer to 15. So this limit equals 15. We already did all the work to find that. This is just kind of the change in notation that we're going to look at in this section. Okay, so let's look at the definition of a limit. We say that the limit of f of x is L. We're just calling the limit L. as x approaches, oops. As x approaches a, Mm. And we write this as the limit as x approaches a of f of x equals L. Can everybody still see? Should I turn the lights back on? Nobody cares one way or the other. Okay, I'll give you all a second to copy that. It just says that is provided we can make f of x as close to L as we want for all x values sufficiently close to a from both sides without actually letting x be a. We'll talk about what that means here in a second. Basically, all this is explaining is kind of the chart that we've been doing in examples where we took values that got closer and closer to the x value that we were given. And then the values that we saw come out of that, we're getting closer and closer to a specific number. All this is saying is that when we plug in numbers that get closer and closer to our x value, then when we plug it in, it should be getting closer and closer to our limit. Which that's how we found this value before, is by looking at what those numbers were getting closer to. Now we're saying those numbers have to be getting closer and closer to the same number as we get closer and closer to this x value in order for that to be the limit. It's just kind of explaining further what we've already done. Okay, it's also important, this from both sides is important. So when we did our chart, we looked at values getting closer and closer from the left side and closer from the right side. We have to look at both of those every time. We can't just look at one side and call it good. Okay, let's go ahead and work an example. Okay, estimate the value of the following limit. Trying to decide how I want to write this. The limit as x approaches to of x squared plus 4x minus 12 over x squared minus 2x. The limit as x approaches to of x squared plus 4x minus 12 over x squared minus 2x. Okay, so we're gonna work this problem the same way that we've been working these. It's just that we don't have to do the work at the beginning that finds this equation. Like we don't have to find the slope or anything. We're using this equation to plug in our values in our chart. So if we want x values that get closer and closer to 2, if we go from the right side of 2, we'll start at 2.5 and go to 2.1, 2.01, 2.001, and we'll go one more. Okay, and we're plugging those into this part of our limit equation. And let's go ahead and call that f of x, since that's what it's called in our definition of the limit. Okay, then we need to also look at x values on the left side of 2 getting closer and closer. So let's start at 1.5 and go to 1.9, 1.99. All the way down to there. We're going to plug those in and get values of f of x. Okay, I don't want to take the time to let you guys all plug these in. So let's just do a couple together and then I'll give you the rest. So to plug this in, I would plug in a fraction first, alpha y equals, to get a fraction put in. And then if we were doing 2.5, that'd be 2.5 squared plus 4 times 2.5 minus 12 in the numerator. And in the denominator, we'd have 2.5 squared minus 2 times 2.5. We get 3.4. Okay, so from there, you would just use this same equation and go back and change all the 2.5s to 2.1. And we get a lot more decimal places this time, 3.857,142,857. When we plug in 2.01, we get 3.985,074,627. Plug in the next one and we get 3.998,500,750. On the next one, we get 3.999,850,007. On this last one, we get 3.999,985,000. Okay, so plugging in all those numbers, what does it look like our limit is going to be? 4. So these numbers are getting closer and closer to 4. Let's check and make sure on the left side of 2 that the same thing is happening. Okay, if we plug in 1.5, we get 5.0. Then we get 4.157,894,737. Then we get 4.015,075,377. Next one, we get 4.001,500,750. Okay, the next one we get 4.000,150,008. Last one, 4.000,015,000. Okay, so all of those numbers are also getting closer and closer to 4. Okay, another thing to note is in our definition, we said we don't want to actually let x be a. So we don't want to actually plug 2 into this function. We just want to plug in numbers that get closer and closer to 2. If we were to actually plug in 2 to this function, you don't have to write this, but just if we were to plug in 2, we would have 2 squared plus 4 times 2 minus 12 over 2 squared minus 2 times 2. Okay, that gets us 4 plus 8 minus 12 over 4 minus 4, which would be 0 over 0. I don't like this example. This is an indeterminate form. We're going to talk more about 0 over 0 later.
Teachers and students, please excuse this announcement. At the end of this announcement, we will have our mandatory monthly fire drill for the month of September. Again, this is the mandatory fire drill. And those students and fire marshals, please report.
Okay. So we plugged, or I did, you guys didn't have to write this, but when we plug 2 into this function, we get 0 over 0, which I said we'll talk about later. The important part is we have a 0 in the denominator, and you can't have division by 0. So this is just to drive home the point that we're not looking at what's happening at 2. We're looking at what's happening as we get closer and closer to 2, or to whatever x value we're given. Okay, and so our chart tells us that as we get closer and closer to 2, the function value is getting closer and closer to 4. So we can say the limit as x approaches 2 of x squared plus 4x minus 12 over x squared minus 2x, this limit equals 4. All right, I want to take a look at what is happening on the graph of this function. Okay, so here's a rough drawing of what our graph looks like. And we said at an x value of 2, we got division by 0, which actually causes a hole in the graph. So I'm going to draw that in. So we have a hole in the graph where x equals 2. You can see that's where our 2 is. So as we were plugging in our x values into the function, we plugged in numbers on the right side of 2 that got closer and closer to 2. So we started at 2.5 and got closer and closer to 2. Then we started at 1.5 and got closer and closer to 2. That's supposed to be an arrow. Yeah. So when we're computing limits, we're not really asking what's going on the graph at 2, because if we were asking that, we would say, well, it's undefined because there's a hole in the graph there, because when you plug in 2, you get division by 0. But a limit is only concerned with what's happening on either side of 2, or whatever number, whatever x value we're given. So on either side of 2, our function value is getting closer and closer to 4. Even though f of 2, or the function, doesn't actually exist when x is 2, our limit still exists because on either side of 2, the function is still getting closer and closer to that y value. So just remember that limits don't care what's happening at the point in question, it cares what's happening around it. Okay, I'll wait until next time to do the second example.